Hey there, in this video, we're going to look at some substitution methods that we can use to solve some types of differential equations. Specifically, we're going to look at two different types of substitutions, homogeneous and Bernoulli equations. And this is going to be our general strategy for solving them using a substitution. First, we got to identify which type of equation we're dealing with. Is it homogeneous or is it a Bernoulli? And we'll go over both of those definitions. And then we're going to have a specific substitution that we're going to do based on the type. And so we'll use that substitution to rewrite the equation using new variables, much like we do like a U substitution when we're going to integrate. And then we're going to solve that equation. The equation should be reduced to a linear equation at that point, which means we can either use separation of variables or an integrating factor to solve it at that point. And then we just reverse that substitution to get back to our original variables. So that's kind of our overall strategy for these. Let's start with the first one, looking at homogeneous equation. Okay, so we have a new definition. We're using homogeneous a little differently here. I know it's terrible that we're using the same term for two different things, but this is different from the homogeneous that we've talked about before, where we have a differential equation such as dy dx plus some function of x times y equals 0. We have a 0 on the right side. So it's a different kind of homogeneous that we're looking at when we're talking about these kind of substitutions. A homogeneous function in general, or equation, not even a differential equation, just any equation, we would call homogeneous. If when I replaced x and y in the function with tx and ty, if I'm able to actually factor out a power of t from the entire equation, then we say it's homogeneous. For a differential equation, we can see down below there. If I write it in that form, kind of like exact equations, if you've seen those, if I can take those two equations that are multiplying by my differentials, the dy and the dx, and I can plug in a tx, ty into both of those and factor out the same power of t from both of them, then we would say that, that the differential equation is homogeneous here. Okay, so just to wrap our heads around that definition, let's look at an example of just a plain old function, not even a differential equation, and see if we can prove or figure out whether it is homogeneous or not. So I've got f of xy is equal to x to the fourth plus y to the fourth. So I'm going to replace x and y in the function with tx and ty. And so my function looks like this. So I have tx to the fourth plus ty to the fourth. Now I could distribute the powers to the t's and the x's and the y's there, and then factor out the t to the fourth. The t to the fourth, and rewrite this equation as t to the fourth times x to the fourth plus y to the fourth. And so I was able to plug in t along with the x and the y, and then factor it out completely from the whole function without changing anything else about it. So I can say that this meets that definition of homogeneous equation. And so this is a homogeneous equation, and because it's a fourth power that we were able to pull out, this one is of degree 4. So that's what we're talking about when we're working with homogeneous equations and the specific type of substitution we're going to do with them. The degree doesn't really matter so much as long as you can factor out some power of t from them. So if you're not told that it's homogeneous, then we've got to check this for both of the equations m and n that are in a given differential equation. Okay, so if I've established that I'm dealing with a homogeneous equation, then I'm going to use one of these two substitutions for it. So either y equals u times x, so I would replace all the y's in the equation with u times x, or x equals v times y. And in both of these cases, the u and the v are new independent variables or dependent variables that we're not really going to define. They're just going to be a placeholder so we can change the look and form of our differential equation so that we can turn it into something that's linear, so that we can solve it using separable or sometimes integrating factor. Okay, now I'm going to be substituting this into a differential equation, which means if I'm taking out, for instance, with the first substitution, if I'm taking out y and replacing it with u times x, I also have to replace dy. So I need to know what the dy would be equal to in the substitution in terms of u and x. So it's just a quick product rule to get that derivative. So derivative of u times x would be u times the derivative of x plus x times the derivative of u. So we get dy equals u dx plus x du. The nice thing is this is the same every time. So if you've got these, if you just keep these together, when you're doing the substitution, you'll use both of them. For x equals v times y, well, doing that same product rule, I get dx equals v dy plus y dv. Okay. Now, if we're wondering, well, okay, when do I know which one of these to use? Well, basically, we look for the path of least resistance here, looking for the easiest way to do this. So if the n is simpler, because n is the one that multiplying by dy, then that's the one I'm going to use the y substitution there. If the m is simpler, so the part that's multiplying by the dx, if that's simpler, then I will use the replacement there. And simpler usually means like fewer terms, because I'm going to have to do a lot of distributing if I'm replacing, the differential with this product rule now. So we go for the simpler one just to make life a little easier. Okay, so let's do an example with this. So here I have an equation. They're telling me it's homogeneous. I'm going to check it anyway just for a little extra practice. So I got x squared dy dx equals xy plus 3y squared. Now, first thing I want to do is get it into that form that we liked before, where I have m times dx plus n times dy. So I can check for to see whether it's homogeneous. So if I do a little messing around here, I multiply both sides of the equation by dx and then move everything to one side of the equation, I get the quantity xy plus 3y squared times dx minus x squared dy equals 0. So this is in a form that's more recognizable, where now I can look and say m is going to be xy plus 3y squared, and n is going to be negative x squared. And I'm going to test these for homogeneity. So if I plug in tx ty for m, I'm going to get tx times ty plus 3 times ty squared. I can pull a t squared out of both of those terms. Okay, so that one's looking homogeneous to me, of degree 2. Let's do the same thing with the negative x squared. So replace that x with tx, so negative tx squared. Well, I can pull the tx squared out of that as well. So both of these are homogeneous equations of degree 2, which means the differential equation itself is a homogeneous equation. So now I know I can do the substitution. It should work out really nicely for me. Okay, so I'm going to go back to my original equation here. I'm told x is greater than 0, which is just going to help me with some absolute values later. But now I know that I'm going to do substitution. And looking at my m and my n, well, the n is a simpler one. Right? X squared is much simpler than xy plus 3y squared. A lot less than I'm going to have to distribute there. So I'm going to go with that first substitution, y equals ux, which means that dy equals u dx plus x du. Okay, so I'm going to go through this equation and start rewriting it. Every time I hit a y, I'll replace it with ux. Every time I hit a dy, I'll replace it with that product rule. So it looks something like this. These get a little messy sometimes, but I've replaced all of the y's and the dy's with ux's. And if I start looking at this, I can distribute everything out. I notice I have a negative ux squared that's going to be multiplied by dx. And in the second term, I've got a ux squared dx as well. So those are actually going to cancel out. And I end up with just negative 3u squared x squared dx plus x cubed du from distributing the x squared in that second term. Okay, so you might want to pause this for a second and distribute that out and see how I simplified it, but it did clean it up a little bit. You usually should get something combining when you do this. If nothing's combining, then double check your substitutions. Okay, so now, believe it or not, I have a separable equation. So I'm going to start separating the variables. So I'm going to throw, the differentials on opposite sides. So I have the du term on one side and the dx term on the other. And then let's see, to get these separated, I'm going to have to divide by x cubed to get the x away from the left side. I'm going to have to divide by u squared to get the u away from the right side. So that is going to give me du over u squared equals 3 over x dx if I combine those x terms. Okay, I've separated the variables. U's are on the left, x's are on the right, so I can use separation of variables to integrate this. I will integrate both sides of this equation. Integral of u to the negative second is negative 1 over u. Integral of 3 over x is 3 natural log of x with the absolute value on there, plus c. Okay, so gosh, I'm getting close to the end here. It's a long problem, but I've integrated. And so now I can go ahead and solve this for u. And a nice trick when you've got a 1 over u equals something is, well, treat them both like fractions. So the right side is that 3 natural log of x plus c over 1. And if I flip them, well, the fractions are going to remain equal. So that's kind of a nice little trick here to get this solved quickly. And I also moved the negative over to the right side of this. So I've got the u solved for. You don't necessarily have to solve for u before reversing your substitution, but it's nice when you can. So remember that y is equal to ux, which means that u is equal to y over x. So I can replace, I skipped a step there. Sorry, there should have been one in between. So u was y over x, and then I multiply that x over to the right side of the equation to get the y by itself. I also dropped the absolute value off the x because I was told that x is positive here. So I can just make it a little bit simpler. And I've got my answer. Okay, so it's going to be kind of long and overwhelming, but once you get the hang of it, they will speed up a little bit. Okay, so those are homogeneous equations and how I would solve those every time. Next thing we want to look at is Bernoulli equations. So these are a little different in their form. I don't have that m and n form to it here. It's going to be dy dx plus p of x times y equals some function q of x times a power of y, so y to the n. So these kind of remind me more of when we did integrating factors. If you're familiar with those, we tend to use integrating factors when we solve these. Not always. Separation of variables might also work as well. But if you have it in this form, where I've got the derivative plus a function of x times y equals a function of x times another power of y, then this is a Bernoulli equation. So if the n, that power of y on the right is 0 or 1, it's a linear equation already. I don't need to worry about a substitution. If it's something other than 0 or 1, that's when I need to worry about doing some kind of substitution to get this into a linear form. And the substitution we're going to use here is u is equal to y to the 1 minus n. So whatever that power of n on the right is, I'm going to do 1 minus that and stick that on my y. And using this substitution should give me a linear equation. I will need to do a differential of this, but it's going to be different every time because I'm going to have a different power of y each time. So let's do an example where we can see how this works. All right, we want to solve the Bernoulli equation, dy dx plus 6y equals 30y to the 2/3. Okay, so it's definitely in that form. I have the derivative plus some function of x, which there's no x in there, but I have a function times y equals some other function times y to a power. Okay, and notice the power does not have to be an integer. 2/3 is also going to work, does qualify as a Bernoulli equation. Okay, so substitution I'm going to do. U is going to equal y to the 1 minus 2/3. Okay, so my n is the 2/3, so 1 minus that, that's going to give me y to the 1/3. So u equals y to the 1/3, and sometimes it pays, particularly with a fractional exponent like this, to go ahead and solve this for y. So if u equals y to the 1/3, then y will equal u cubed, just by cubing both sides of that equation there. Right? I don't always do that, but you can often do that. It does change the way your differential looks, depending on which one of these I'm taking the derivative of. I'm going to go ahead and take a derivative of the bottom one. If I take the derivative of the top one, then I'm probably going to end up multiplying my equation by something. So you want to look at more examples of this to see variations of how you might do the substitution. But here, I'm going to go ahead with the easier way and to take the derivative of y equals u cubed. So dy dx is going to equal 3u squared times du dx. So I'm doing a chain rule there. I don't know what u is. So I've got to have the derivative of the cubed function times the derivative of u there. And so since I know exactly what dy dx is equal to, I can just substitute that in. If I had this equation flip-flopped where it was du dx equals some function times dy dx, then I would be multiplying by that function. So like the 3u squared, if that was multiplying by dy dx here, I would multiply the whole equation by that just to get it to match up for my substitution. For us, we can go a simpler route here. I'm just going to swap out dy dx for 3u squared du dx, and then swap out all of the y's for u's here. So replacing everything, I get 3u squared du dx plus 6 times u cubed plus 30 times, and I'll be careful with this one, I'm replacing y with u cubed, and so u cubed to the 2/3. That'll simplify to u squared. Okay, believe it or not, I have a much nicer equation. I notice I have at least a u squared in every term here, and a common factor of 3 going throughout, so I'm going to reduce this by just dividing by 3u squared. Cleans things up a little bit, just makes life a little easier. So I've got du dx plus 2u now equals just 10. So a lot nicer and a lot more obvious that this is separable. So I'm going to go ahead and start separating those variables. If I subtract the 2u over to the right side and multiply by dx, I get du equals 10 minus 2u times dx. And then to separate those variables, I'll divide by 10 minus 2u. Okay, so now I have something ready to integrate. My u's are on one side, the x's are on the other side, and I can integrate this. Again, I'm going quickly through this because it's a longer problem. That u substitution on the you do want to do a u substitution on the left here, but you should end up with -1/2 times the natural log of the absolute value of 10 minus 2u on the left side, and then just x plus a constant on the right. I'm going to call that constant C1 because this is going to change as I solve this. So I want to denote that as I go by changing the subscript on that constant of integration. Okay, so to solve this, there's a few different ways to do it. I'm going to start off by multiplying by the -1/2, getting rid of the -1/2 on the left. So I'm going to multiply by -2 on both sides. And get my C changed to C2 now because I multiplied it by a constant. And it cleaned things up a little bit. If I use E to raise both sides, I'm going to get just 10 minus 2u on the left. I'm going to take the plus or minus and everything and throw it into a new constant that's multiplying by e to the -2x now. Okay, so I'm doing a little bit of algebra there. You might want to take some steps to write that out if you get a little lost there in between those two steps. And I am almost there now. I can just subtract 10 from both sides of the equation and then divide by -2. Okay, and then I get my final constant folding in that -2 in the first term. So I'm going to call it just C now. So u equals C times e to the 2x plus 5. And almost done. I just need to get back to my original variable. So remember that u is equal to y to the 1/3. So I can replace that on the left now that I've solved for it. And if you want to solve this explicitly for y, I can cube both sides of this equation to get y equals c plus e to the -2x plus 5 cubed.